You ever wonder how an outfielder just knows where to run to catch a fly ball? Or how a video game figures out that perfect arc for a grenade toss? Well, it's not magic, and it's definitely not guesswork. It's all physics. And today, we're going to break down the super simple, kind of elegant rules that are behind every single curved path you've ever seen. All right, let's get into it.
And once you start looking, you see these paths absolutely everywhere. You know, a football soaring towards the goalposts, that graceful arc of water in a fountain. At first, they look super complicated, right? So how in the world can we predict where something's going to land? Well, turns out, physics has this brilliant little trick up its sleeve.
And the secret isn't some ridiculously long equation or anything like that. No, it's way simpler. It's all about changing how you look at it. You just have to stop seeing it as one complex path. The real trick, the big aha moment, is to see it as two totally separate, way simpler movements that are just happening at the exact same time.
Right, and the tool that lets us split that motion apart, this is what I like to call a true physics superpower. It's the key to understanding all this, and it's called vector decomposition.
Okay, so what's a vector? Don't let the name scare you. It's just a fancy word for something that has both a speed and a direction. And this superpower vector decomposition lets us take any motion and just break it apart. We split it into two simple pieces. One part that's just going sideways, that's our horizontal or X part, and another that's just going up and down, our vertical or Y part. The cool thing is, once you figure out those two easy paths, the complicated one basically solves itself.
Now this is where it gets really, really interesting. These two motions, they pretty much live in different universes, each with its own set of rules. Think about the horizontal motion. It's just cruising. It's on a lazy river, totally unbothered. Why? Because gravity doesn't pull things sideways, so its speed just stays constant. But the vertical motion? Oh, that's a whole different ballgame. It's in a constant fight with gravity. It's getting yanked down the whole time, slowing down as it goes up, stopping for a split second at the top, and then speeding up all the way back down. So what happens when you put these two things together? You take that steady, boring horizontal cruise, and you combine it with that dramatic, up and down battle with gravity. What do you get? Well, you get something beautiful. A perfect, elegant shape that you see everywhere. Anything that's thrown or launched into the air, and then the only thing acting on it is gravity, we call that a projectile. And when you combine that simple sideways motion with the vertical acceleration from gravity, its path will always, and I mean always, trace out a perfect parabola. It's like the signature shape of motion here on Earth. Okay, so to talk about these parabolas, we've got a few key terms. It's like learning the language. First step, time of flight. That's just what it sounds like. How long is the thing actually in the air? Then there's maximum height. That's the tippy top of the arc, that one moment where it stops going up and starts coming down. And finally, range. That's the big one for a lot of things. It's just how far it travels horizontally, from start to finish. So we have these two completely separate journeys, the horizontal and the vertical. What's the one thing that ties them together? It's time. This is the crucial point right here. The object is moving sideways for the exact same amount of time that it's moving up and down. That shared time of flight, that is the golden key. It's what lets us connect the two motions and solve the whole puzzle. Okay, so we've got a handle on how to break down an object's motion. But now let's add a bit of a twist. What happens when the person watching the motion is also moving?
This gets us right to the heart of something called relative velocity. So picture this. You're on a speeding train, and you toss a ball straight up in the air. To you, inside the train, it just goes up and comes straight back down into your hand. Easy. But what about your friend standing on the platform watching you go by? To them, that ball just traced a massive parabola as it flew forward with the train. It's the same ball, the same exact throw, but two totally different paths. It all depends on your point of view.
All right, let's try the classic riverboat problem. Imagine you're driving this boat. You want to get to the dock that's directly across the river, so you point your boat straight at it and hit the gas. But the river has other ideas. There's a current that's constantly pushing you sideways, downstream. So you don't just get your forward motion, and you don't just get the river's sideways motion, you get both at the same time. And what's the result? Your boat ends up traveling on a diagonal, landing way downstream from where you were aiming. And this explains something we have all experienced. You know how when it's raining and the rain is just falling straight down, the moment you start running, all of a sudden it feels like the rain is coming at you from the front, hitting you right in the face. The rain didn't change direction, you did. Your forward motion added to the rain's downward motion creates that diagonal effect.
That's relative velocity, right there. Okay, so we've got this awesome framework for how different motions add together. So let's put it to work. Let's use it to answer a really practical question, one that athletes and engineers have obsessed over for, well, forever. Let's say you can throw a ball at a certain speed. That's your launch speed, and it's fixed. What's the best angle to get the absolute maximum distance out of it? Do you fire it off on a low, fast line drive? Or do you launch it way up high so it hangs in the air for a long time? Where's that perfect sweet spot? Well, just take a look at the data. If you go too low, say 30 degrees, you get a ton of horizontal speed, which is great, but it hits the ground way too fast. Bummer. If you go too high, like 60 degrees, you get a ton of airtime, but you're not moving forward very fast. So, what's the perfect balance between hang time and forward speed? Yep, right there in the middle, 45 degrees. That is the magic number for maximum range.
And here's a really cool little bit of physics trivia. Did you notice something weird on that chart? The 30-degree and 60-degree launches, they landed in the exact same spot. How does that work? Well, the 60-degree launch gives you more time in the air, but the 30-degree launch gives you more horizontal speed. And it turns out that for any two angles that add up to 90 degrees, like 20 and 70 or 40 and 50, those two things cancel each other out perfectly. You get the exact same range. How cool is that?
So there you have it, the 45-degree secret for getting the most distance on a nice, flat playing field. But when is the real world ever that simple? Think about shooting a basketball. The hoop is above where you're launching from. That changes things, right? Or what if there's a headwind? Or you're trying to hit a moving target? How do all those little factors change the perfect angle? The physics we talked about today gives you all the tools you need to start figuring that out. Now it's your turn to play with the possibilities.